turn that up to where there's going to be a delicate balance between feedback and volume that we've got to strike. But this has worked before, and I've gotten my lab mic, which if anybody's ever come to this before, you know that I whinged for a long time about not having lab mics. Maybe a little bit louder. That's all I get. Well, you can bring the ramp up. It's going out through that. That is volume 2. Whoa! Okay. Hi, everybody. I'm Matt. I'll try to talk loud over the feedback. Was that an A440? All right. Awesome. Hi, everybody. I'm Matt. Welcome to Didactic Galactic. For those people that are new, just really quick background. So when we decided to start this meetup, it was largely because most of the stuff that was going on in the city was very sort of hand-wavy. There was a lot of people talking about companies that they were building and all of those things, and there was nothing wrong with any of that, but we wanted some place where people could actually go and talk about real engineering stuff. So this will probably be much more practical, much more sort of hands-on, much more detail about like real electronics and building real shit than it will be any sort of hand-wavy thing. We've got the hand-wavy bit in the beginning, but that's okay. We try to keep that short. Just really briefly, so Didactic Galactic is sponsored by the company that I work for, which is SupplyFrame, which happens to be the parent company of Hackaday. Yay, Hackaday! Which, if you've never read Hackaday before, you should go to Hackaday and check it out because there's a lot of really cool projects. People are building a lot of cool stuff, and it's a really cool community of people that are really building interesting shit and trying to get stuff off the ground. If you haven't seen Hackaday.io yet, that's actually the project site for Hackaday. And it's just a place where people can kind of go and collaborate and build projects and share things. It's pretty well attended at this point. We're getting close to probably 100,000 users on Hackaday.io. Am I correct? So there's a lot of people actually building stuff and participating in that space, and we're really excited about it and just really enjoy it. We launched the Hackaday Prize last year. Last year, top prize was a trip to space for $250,000. This year, top prize is similar to that. We also have a best product prize. We're actually going through the process, but if you're interested, jump up onto the Hackaday.io site and take a look at some of the prize entries because they were actually really interesting and really cool. Just a brief bit of news. Hackaday acquired Hddg. Yay! And it was a very amicable coming together of things. And I just wanted to take like 2 seconds just to mention that, you know, part of the motivation in acquiring Hddg and also with the opening of the Hackaday store, which we did recently, has been really all motivated in a very genuine way around how do we actually create economic opportunity for people who want to build stuff. So if you have something that's cool that you've built, that you've designed, and you want to get some social proof, maybe it's kind of before you go off and you launch the crowdfunding campaign or anything like that, you can put it in Hddg, see if people like it, work on it, revise it, see if people will buy it, and sort of improve the product from there. Meshing that with what's going on Hackaday.io, there's a great community there of people that can kind of talk about what it is that you're working on, what the product is, what features it might need to have, what parts you might want to source for something here or there. And then ultimately, we've got the Hackaday store, which actually I have umbrella responsibility for both Hddg and the Hackaday store. And the Hackaday store, just for those people that don't know about it, it's just store.hackaday.com. But I'm actually looking for new products to stick into the Hackaday store. So what that means is that if you have something which is cool and it's interesting and it's the kind of thing in which you think the community, particularly the Hackaday style community, might actually be interested in, like if you're a nerd like me or some kind of geek who finds it really hard to get Christmas presents from anybody, this is one of those places where you can actually sort of shop for that sort of stuff. So if you're building something which kind of falls along those lines or might be useful to people who are trying to build electronics, come and see me afterwards, whatever. You know, that's one of those things that's relatively easy. If it's a cool, sort of fully realized thing, and it's relatively open, and it's available to the community for people to be able to play around with, I have no problems writing a PO to somebody and buying a bunch of pieces and seeing how it actually works in that space. So that said, that's kind of it from the announcement side. The Hddg thing was really cool, and for everybody who's afraid, we're not going to change anything on Hddg. The only thing that we'll do is fix all the bugs and implement all the features that everybody ever wanted, or something along those lines. This is the CTO, so I have to be really careful. Other than that, tonight we have some really cool talks lined up, and I think I'll hand it over to Chris Campbell. Chris, you can introduce people and get people lined up. Is that cool? Chris Campbell, host of the Empower podcast. If you don't listen to the Empower, you absolutely should. He and Dave Jones rant for an hour about absolutely anything. They get some amazing people to talk on the show. And it is the best way to kill an hour and not think about how bad your legs hurt when you're running. So I'm just going to go on record as saying that. So, Chris Campbell. Oh, you can't disconnect myself. Some kind of engineer I am.
All right, so first up we have Tom. Tom is from, Tom, what's it called these days? Is it HP or Agilent? Keysight?
I think it's called Keysight.
Keysight. Bill and Dave's garage.
Let me check the time.
Delicious electronic gear. So Tom's going to talk to us a little bit about thermal design and open source tools, and maybe have some interesting things to mention about that. I'm really looking forward to it. Let's give Tom a hand.
I normally talk really loud, so I'll probably have this in buzzing before you know it. So I'm always obligated to say I'm, of course, speaking for myself and not Keysight here, because that's the sort of thing I'm supposed to say. So does anybody here actually already know all about thermal design? Is everybody already ready to go? Are we done yet? Tell us. Okay. So I'm just going to go through the basics of thermal design first, what it is, and then show a couple of examples, and then talk about a little bit about some software. So you got your heat transfer, and that's things like conduction through the copper. You got your convection, your hot air rising, forced air with the fan. Maybe you've got a heat pipe. This is an example of a heat sink with a heat pipe in the middle. And so you put this on the top of a big old processor and blow a hurricane of air across there, and it'll probably take, I don't know, 70, 80 watts out of the thing and have maybe a 5-degree C rise. So this works pretty good. So that's an example of the heat pipes boil on one side and use the vapor to move the heat. So when do you need to worry about thermal? Anytime you have a lead on a board, you should worry about thermal, because they're actually very sensitive components. They really only go up to, I think they're rated usually up to like 85 C or something like that. They're not nearly as rugged as normal semiconductors. Resistors, if they have any power in them. Anything that's in series with the power supply, like a voltage regulator or an inductor or something. And anytime you see the word termination, you know it's going to be hot. Because they all are. Or anytime the word core comes up, multi-core computers, they're all hot. Video, power, or the word thermal, you have to watch out. Once you see those words, you got to do some calculations. And so you have your basic thermal resistance, rho L over A. That's the resistance along the length of the pipe. You take the cross-sectional area on the front, and you get the material property. Now, mechanical engineers like resistance because we're used to resistors. That's electrical engineers like that. Mechanical engineers like the G, because that's the conductance, and that's actually a better number to use. But the electricals like the R because you can make a thermal network, and it looks like something you already know how to solve. And so the resistors are also sometimes called theta instead of R, but that's your degree C per watt. And so you can have this perfect, nearly perfect electrical analogy where current is power. So I have a current source, I1 there, going into the resistor R1, which is some thermal resistance, and it heats up to some temperature, which is represented as a voltage. And what I have here is the ambient temperature. Oh, I'm on the wrong slide. Slides are going the wrong way. There we go. So you got the voltage there, and if you have a transient, then the capacitors charge up. That's a heat capacity. And I'm not going to talk about transient today, just steady state. Be another talk to talk about transient. And then there's fans. And so what people want to know is, do I need a fan or not? So what does a fan do? Well, of course, it blows air. And it's got a curve for how much air it moves. And so the air volume that it moves is on the x-axis here, going to the right, with more air volume. And then the pressure is the y-axis. And so if the fan is blocked, there's no air moving, but you've got some pressure. And then if you put the fan on a duct, a long duct, you get a little bit of flow, and you still have a lot of pressure. And as the duct gets shorter, you get less pressure and more flow until you're just in free air, and then you have no pressure at all and just the flow going through it. So you have these curves that you can design with. And then there's more curves about fans. There's you can try to find the spot where the fan is the most efficient, where it has the optimum power, electrical power that you put in, puts in, does a certain amount of work on the air. And so you'd like to be at some optimal point. And then once you know how much air you really have to move, that's based on how hot things are allowed to get. You can reduce the fan speed down to move just that amount of air, and that really helps with noise, because people don't like noisy fans. So so you get these curves in the data sheet. So if you look at a data sheet for a fan, it's got this curve, which is this pressure volume curve on it. And so you get a wiggly line, but it could be a straight line, because sometimes that's all you get. They just give you these 2 points here. On some of the data sheets, like this one here, it's just got 2 points for and you just draw a straight line between them. Now the problem with fans, when you put them in a box, is you get dead spots where there's no air moving and the fan's not doing any good. And you could buy some really expensive software and do computational fluid dynamics and have a really good time with your computer, or you could make a little tiny flag out of like a stiff piece of wire and a little thread or toilet paper or something like that, and you could bend the wire all around, and you make a mock-up with a window in it so you can see, and you wave the little stick around and you see the little flag moving, and you tell it the airflow is turbulent or laminar or whatever, and you can beat the guy at the computational fluid dynamics by about probably a factor of 10. You'll get a better answer, and you'll save a lot of money. And have a better time on it. And then there's heat pipes, and heat pipes are great, and they're in all your laptops. I haven't seen enough projects where people like take the heat pipe out of a laptop and do something cool with it. I've seen a few, but there's a lot of opportunity there. There's a lot of old laptops out there. So typically there's a liquid like water or alcohol in there, and it's at reduced pressure, so it has a lower boiling point. And so the water, or the liquid is actually boiling on one side of the tube where the chip is, typically like a processor, and then it goes through the tube and condenses at a heat exchanger, also known as a heat sink. It's not really a sink because the heat doesn't disappear there. It's got to be exchanged with air, right? So how about those heat sinks? So I'm going to talk about heat sinks for a minute now. I'm done with fans. So how big a heat sink do you need? Because they make, really big ones and little tiny ones. What do you need? And so I have a rule of thumb, a scientific guess for how to size a heat sink. And that is, if you don't have any fan, you can think of whatever the surface area of your heat sink is in inches. It's 140 degrees C per watt divided by that number of inches. So if you put a fan on it, it's about 10 times better. And you can look at data sheets for heat sinks, and you can see, if you look at the curves and you figure out like this one is like, this particular heat sink is an interesting one. This works in any orientation. So maybe you're designing a card and you don't know what kind of system it's going to go into. So you get one of these heat sinks that just has the spikes on it instead of the fins. Because if you have fins, you're supposed to blow the air along the fins. But if you don't know which direction air is coming from, or if it's convection, and you don't know which way it's up, because convection is all about the buoyancy of air, and the hotter air having weighing less, it tends to float up and causes a little bit of wind that way. So in this case, it's got these posts, and it says what the surface area is, and you can figure out, it actually comes out pretty close. You can convince yourself that's true. Here's one with fins, and it comes out to the, now I didn't say how fast the air was moving for my 14 degrees C per watt, so I can always pick a spot on this curve where I'm right, based on what the airflow is here. Now, you also notice this is the cooling kind of leveling off as the airflow keeps getting more. So it doesn't always work to just keep turning up the fan. At some point, you just end up making a lot of noise, and it doesn't really get anything much cooler. So here's some tricks when you're designing a circuit board to not need heat sinks maybe, or to use thermal parts really well. So if you have a hot part like a resistor or a lead, you put the wider copper traces on there, maybe a 30 mil trace where you might have had a 5 mil trace. Widen it out, and that'll pull a lot of heat away from the component. And so you have to understand about how thick the copper is on the top of the board, because if they plate it up more, you're going to get better heat transfer out of it. Aluminum parts conduct heat really well. So I think of them like a short circuit almost for thermal networks. If you have a nice aluminum enclosure and you probe around on that aluminum enclosure with a thermometer, it's about the same temperature all the way around. And then air gaps are really bad. Even if it's 1/1000th of an inch of air, it's going to have a lot of thermal resistance. So you put in the goo, the thermal grease or whatever. So I'm going to do a couple of examples of thermal networks and designs. And what I don't know is if people have already been through all this already, so I'll just do one, and then if everybody already knows all this stuff, I'll skip this second one. So say you had a voltage regulator, and you've got your adjustable regulator. It's got the 2 feedback resistors that set the output voltage, and I'm just going to do something simple. I'm going to say I got 15 volts in and 12 volts out, and I don't want it to be hotter than a 30 degrees C rise above my outside temperature, and I just want to use recommended layouts. I don't want any surprises, and I just want to know how much current do I get out of that, and so we can figure that out. And so on the data sheet, they have these numbers. Each of these packages has its own thermal resistance number in it, and so I see those numbers are between 30 and 70 degrees C, depending on which package I pick. So I make the thermal network, and I've got a pretty simple circuit. It's got a current source. I don't know what the power is in advance. That's what I'm trying to calculate, because I know the temperature I've got, I know my resistance. So I know my voltage and resistance. I'm figuring current Ohm's law. So that comes out to, if it's 30 degrees C rise and 30 degrees C per watt, it's 1 watt. And if it's 70 degrees C rise, it's less than ½ a watt. So I also know I have a 12 volt drop, or a 3 volt drop between the 15 and the 12. So that's 3 volts of DC drop. And so my current, or my power, is V times I. So I know my current is 1/3 of whatever the power is. And so I got an output current between a 1/7 and a 1/3 of an amp. Okay, are we done with the thermal design yet? Did I leave anything out? Anybody spot anything?
I was reading that.
No? Okay. Well, there's this resistor feedback network there. And you can have a lot of fun designing these little feedback networks. I think resistor dividers are probably the most fun circuit, because you get to do them so often. And they have the little adjustment pin here, and it takes a little bit of current. It kind of makes an error term because it varies, but it's small. Now I have a 1K resistor in the feedback here, and that's actually going to have 145 milliwatts in it. So I would probably consider scaling that up, maybe make it like a 10K and a 1K or something like that instead. And Also, if this R1, this 1K, it has another surprise in it that most people probably don't notice because it's in the resistor data sheet. Does anybody here read resistor data sheets? Is that even a thing? Yeah, they are. There is a thing. It's a resistor data sheet, and it's got a bunch of numbers on it. And the news here is pretty bad for cheap resistors. The news is that, yeah, it's a 1% resistor when you bought it, and it's on a reel. When you load it into the board, it's a 2% resistor. And then you age it for 1,000 hours at 70 degrees C. It'll probably be that warm in this power supply because it's a warm design. It's a 5% resistor. And so most people don't know that they're in that situation. And there's a solution, which is you pay 2 cents instead of 0.2 cents, and you get a thin film resistor instead of a thick film resistor. And it has some other advantages too, like if you're doing low noise design, they're lower noise also. But your reel is going to cost you $100 instead of $10. So yeah, it's real money. Any questions on the first example? Is that interesting? Did anybody learn anything? Is this all old? Yeah. Oh, I'm sorry, I can't hear you. My ears are really bad.
Sorry, could you use much higher values?
Yes, I rigged it. It's a rigged demo. Yeah. Actually, though, in real designs, what happens is, based on that adjustment current, sometimes people want to reduce the error term caused by that current, and so they'll set those values a little low. And on the old LM317 designs, it's got the 2 resistors, and they want one of them to be 120 ohms, and then the one going down in the bottom is usually like a K ohm or something like that. And I've seen a lot of designs where that bottom resistor is overstressed in the old 3-terminal adjustable regulators. It's a very common design error. So this one's got the ground pin. And so it's not quite the same design, and so it's the other resistor that's the big one. But yeah, it's a very common design error. So cooling a power FET. So I'm going to say, it seems like maybe that wasn't too bad an example, so I'll do one more. So this is a power FET, and this is what marketing promised us. They said that this little tiny part can dissipate 200 watts, which is really something. You look at that little thing and you say, well, that's amazing. And so let's see what they mean by that. So I'm just going to use a recommended layout for the thing, and they recommend a 1 square inch of 2-ounce copper. That's nice plated up copper on the top of a board. Like if you had fancy Dias or something, it'll plate up to 2 ounces, just normally. Maybe you have 1 ounce copper normally, you ask for a little more. So 35 degrees C per watt, and they want 1 square inch. So here's our circuit. And I'm going to say I want the circuit to work on hot days, maybe 45 C, or maybe it's in a rack and it's hot. So inside my product, there's also some temperature rise inside the box. So I'll give that 15 degrees C. You're going to have some rise in there. And then I've got my 35 degrees C resistor here, and I'm going to let the transistor get up to 150 degrees C. And that's because at 175 C, where they spec it, it's maybe good for 1,000 hours. That's an absolute maximum rating. That's the kind of thing they're good for. It's like 1,000 hours. You need to back down from those somewhat to make reliable electronics. So when I divide this out, I get 2.57 watts. So where's the mistake? What happened? 200 watts to 2.5. How did that happen? Well, let's see where they got that 200 number from. Where they got it from was they said, well, we'll let the part get to 175 degrees, and then we're going to take not that 35 degrees C per watt on a board with the recommended layout. We're going to use just the 0.75, just the thermal resistance between the transistor and the bottom of the case. And then we're going to magically hold the bottom of the case to 25 C. Not going to tell you how we're doing it, but we're going to hold it there somehow. And so then you divide it out and you get exactly 200 watts. So if you go and ask the marketing guy, like, okay, how are we going to do that? How are we going to hold that to 25? Maybe he'll show you this. And that actually works. I think they use that in R&D labs every now and then when they have a hot chip. So cooling a PC board. What if we just said the PC board is its own heatsink? It's a nice plate. Maybe it's a uniform plate, which, you know, uniform PC board, spherical cowl, you know, that sort of thing. So if I go through and do the numbers, I get something like, with no fan, I'm good for 0.2 watt per square inch. And with a fan, I can do, say, 2 watts per square inch. I got, let's say, a 5x5 board. That's 50 square inches because I get to count the top and the bottom of the board as surface area. This doesn't actually work so well. More likely 1 watt per square inch is actually pretty hot because of hotspots. And so just an example of hotspots. Here's a design. It's got a power op amp in it. Ah, the power word. See that power word, you know you have a thermal problem. So I thought, well, I'll put the power op amp near where the air is blowing in because I want to get that nice cool air on the power op amps. And so I got the 4 power op amps here, and I know the air is flowing from right to left here, which is also bottom to top, and I have this air flowing in. The fan is blowing bottom to top, which is really nice, so it's not fighting the convection. So if I have a little bit of convection, it just helps the fan along. Great stuff. Thermal camera measurement. I got hot spots, and it's too hot. But that's not fair because there's all this metal and stuff around the board, and you know, it has this fan blowing on it. It should be better than that. So you put it in the environmental test chamber, put on thermocouples and all that. It's still too hot. It's the same temperature. So you could get some CAD tools. You could go out and buy yourself some CAD tools, and a bunch of people make them. Figure out where those hotspots are. They work the same way. They mesh the board. They cut the board up and chop it up into tiny little pieces and make a model for each piece and put them all together and simulate it and get temperatures. It's just a resistor network. It's not that hard to simulate. So I thought, well, how hard could it be to simulate, you know, a bunch of resistors? Really? I mean, come on. I can do that. So, well, I'll write my own, and I'll just make, but I'm not going to make triangles. I see all these triangles everywhere, and they have problems. I'm going to use little squares. And in the 2D case, they're just like pixels. And now I really have a 3D problem, and so I'm going to need to stack them up. And so say I have a board here, I'm going to have a slab of copper and then a slab of FR4 and so on. And I'm going to connect all the resistors together, and I'm going to make myself a little CAD tool there, and I'll have a lot of equations, so I'm going to need a matrix, right? I'll have a matrix solver. So how about that matrix? Okay, math. You were promised math. Here's the math. So now you see why the ME's like the G's, because you don't have to write the 1 over R's, because we have GV equals I is the equation, and so we have a G matrix and a V and I. And what I want to do is I want to get these V's by themselves over on the left, because I know these currents, these are the powers going in, I know my thermal resistances, and I need to solve for that. So one way to do it is to invert the matrix. And so I did that by hand for this little example, and I came up with some numbers, and I solved for my V's. And one of the things I noticed about having the inverse of the matrix, you can actually solve it without computing the inverse, it's faster, but having the inverse is nice because it allows me to find the blame for what heated up what. So my entries on the diagonal, or on the major diagonal here are the how well the heatsink works for each particular little square. And then the other ones are thermal crosstalk. So that's where one part is heating up another. And so that allows me to assign blame. So if I have one spot and I say, you're too hot, what's causing you to be too hot? The inverse of the matrix will allow me to say, oh, you're getting 3 degrees from this guy, 2 degrees from this guy, oh, 10 degrees from him. I got to move him away. So I like having that matrix. But I have a big matrix. And so I need a big solver. Now, SPICE uses modified nodal analysis, which turns out to be bad for this kind of thing because it needs to solve a mixture of current sources and voltage sources. And what I found was that if I took the Norton equivalent of all the voltage sources and turned them into current sources, the solver worked much better. And it allowed me to use an iterative solver, which can be done on parallel supercomputer style. And that's really cool. So that lets me scale it up. And you can use NumPy to do this. You can use a SPICE. I like using SPICE for test designs because I understand it and I trust the answers. But I listen to the RCE's Supercomputers podcast, right? So I'm thinking I know me something about supercomputers. I listen to podcasts. So it turns out there's this thing called Trillanos, and it comes from Sandia National Labs. It's a big box out in the desert with no windows, and a lot of like high voltage lines going into it, nothing coming out. It's really cool. So they broke the 2 gig barrier for matrices, which is matrices that are bigger than 2 billion rows and 2 billion columns. So they ran out of the 32-bit range on just their count of the number of rows. And I only need about 200 million by 200 million to do a great big board with little tiny squares. And so this will actually fit on a single computer with multiple cores. And so I can get multiple core performance and I don't have to set up a whole network. I can just go to Amazon and EC2 and get a big instance and it can run a big board for not much money. So the input is just a Gerber layout file that converts to a bitmap. And what the code does is just loop through each pixel in the PNG file, the bitmap, and load up a matrix with the numbers that it finds, and then solve it, and then make a picture of the output. And so here's a little simple test design. So this is a bitmap, and in blue I drew, these are boundary conditions. They're held at 25C. The green represents copper traces, and the red is spots where heat gets injected, like from resistors. So each of these pairs of red squares represents like a little resistor with power in it. And they all have the same power. So just looking at this, can you tell which one, where the hotspot is in this? It's kind of hard to know because some of them have a thick trace that you would think, well, that's going to conduct heat away really well. But on the other hand, this thinner trace is connected to this boundary here. So what's better? And this guy down here is all by himself, but he's really kind of the same as this. So, you know, how much is what? Are these things close? Are these things heating each other up? It's hard to tell. Yeah.
I think it's the third one from the top because it might be picking up some heat from the two above it.
Yeah. Anybody else have a guess? Yeah. It's a good guess. Which one? The left one or the right one?
It's still picking up more heat than the one on the very bottom.
True. And there's the profile of it. So this is 1,000 by 1,000 cells, and they did it on a little Mac Mini. It took just like a minute or something to do a million rows and a million columns in the matrix. It's sparse matrix, of course. And so you can get that resolved out, and you can see that that is exactly where the hotspot is. And I drew these two pictures to the side so you can kind of see how it lines up. And the hotspot is in between these two resistors here. Is the hotspot. And yes, they are kind of close. Is the answer. Now this is a 2-dimensional simulation. My code is not ready yet in 3 dimensions. But I'm working on it, and I call it ThermP. And that stands for Thermopythia. It's written in Python, of course. And it's got a BSD license. And Thermopythia, it turns out, is the name for the oracle at Delphi. Her name is Pythia. apparently, independent of her actual name. They call her Pythia. And then Thermopythia, let's see, thermothermy. That's the feminine for thermal, or thermal, for heat. So it means hot oracle. Let's see. Where's my GitHub? That's not it. I have GitHub on here somewhere. Oh yeah, there's GitHub. So here's my repo. And I think I just press this button and make it public. And there it is. We hope. Any questions? All right, thanks.
Let's give Tom another hand. All right, so we're going to do a little bit of quick setup here. We did realize that some of the screen got washed out. That we got the screen, but not necessarily all the time. So we're going to try some lights next time as well for Lisa. So up next is Alicia. She's going to be doing a talk about inertial sensors. She acquired a very exciting toy that she ripped apart and started going through and doing a teardown of, which we'll be talking about here, and she'll be able to tell you all about that stuff. So we're going to take a quick second and get some lights set up, and Alicia will get started. You need a drink, now's the time. It'll turn on. They're all right.
Anybody want to speak stickers? Stickers, anybody? It's more an effort to see how well I can grow with the microphone. Yay, podcast! Do you want me to start?
Ready? See Alicia, a round of applause for.
Hello, I'm Elecia White, and I am here to tell you about inertial sensors because inertial sensors are really cool, and they make movement an intangible interface so that we can deal with humans in a much better way. And I admit that when Chris asked me to give a talk, my first response was, Chris, you've got to be kidding, I don't have time. But I did give this lovely, solid talk, which got some pretty good results. And one of the things that I really wanted to emphasize there was that how inertial sensors work with humans. It seems like magic if you don't understand it. I mean, think about the Wiimotes and being able to turn things. But inertial sensors are even more magic if you do understand it. However, you know how when you call a person, you come up with an idea and you're like, okay, I'm going to ask you a question. It's going to be detailed and technical. You call them and you realize, oh, I know what it is. Just as they answer, you're like, goodbye. So yeah, that's sort of what happened. If you would like to see the original talk, it was the one that I gave it solid. You can search online and find it. It's on YouTube. I was gonna take out a little bit of intro stuff and then add a few things from this really nice Kalman filter write-up that I got. But yeah, so then life intervenes, other things happen, and so this is what I'm gonna talk about instead. The BB-8 robots that came out for Star Wars, the new toy, is based on Sphero, and so it probably looks pretty familiar. It's not even that different from Sphero other than the magnetic head, and yet so cool. There have been a lot of people who have already looked at these, who've broken them apart. Chris is not here. Hi Chris, I know you're online. So I'm not going to say anything, but if you ever listen to the podcast, you realize Chris doesn't always leave the house, so it's up to me. But there were other people who looked at the BB-8s who took them apart. You break it, I fix it, did a 2-minute video where they grumbled it apart. It was pretty cool. And they show some of the guts. CNET did a longer video. Let's see who's that. Bill somebody? Bill Dwippler. Sorry, Bill. That's totally. They did a nice teardown, about 5 minutes, that talks about what's going on inside of cracking it open. Even these other people who really did a brilliant job of showing you all of the mechanicals, neat if you want to look at it. But my background, embedded software. So I don't really care about the screws. I don't even really care about the motors, I'll admit it. I mean, stepper versus DC, all I want to know is what was the chip? In fact, what was the inertial chip was my first question. I am not the first person to consider how you build these. The physics of them are quite interesting, and XKCD did a pretty good job. They did a better job than, I'm sorry, you're trying to take pictures and I'm flipping around, aren't I? So these people looked at patents and tried to consider how you would put together a BB-8 to work like this. And if you look here, 1, 2, 3 sets of motors. So that's 6 motors. If you've ever worked in consumer toys, you'll know that that's just hilarious. There's no way they're going to afford that. No, these puppies cost $150, which is a lot. They're so really cute, and I can believe that the $250 scalpers are going to get it for Christmas. If you look inside, which I have done for you, you will see that there are only 2 motors, and we'll look a little bit more about how that works later. do get some clues about the internals from the application. We know that they have at least one accelerometer, that's sort of a given. They do some neat stuff with the gyro where you can actually see the guy move. And that's more of an accelerometer thing than a gyro thing, but it's still pretty cool. There are actually 3 different ways to look at the gyros inside the application. But they also do dead reckoning using the accelerometers and gyros. It is exactly what you would expect from integrating some accelerometers and some gyros, which is to say, it's not very good at all. So it also, in the law, check this with the here, it claims it has an IR sensor. It claims it can detect humanoids. And yet it detects a humanoid just as often when it hits a chair as when it hits my foot. So I am not betting on that IR sensor, and I never found it. So once you have one of these, and you play with it for a few minutes, it's really easy to bond. I mean, they're just really cute. And he nods, and he just has all of these behaviors that are built in. So, of course, my first impulse, yeah. A little bit of trembling, that's all it takes. It was a little terrifying. The whole time I could hear him in my head going, no, disassemble. But I did want, I am the sort of engineer who didn't take apart their toys as a child. I build things. I was a reader, and I tend to get blocks and want to build things up. And I never was very good at looking what was in something, except unless I smashed it, and then it's not as interesting. So this was the first time I sat down and thought, how am I going to take this apart in a way that really is instructive to me? And it was me. You Hackaday people are cool. So opening to the creamy goodness inside. Like I said, I wasn't that excited about the mechanical. Not to say that there wasn't some interesting stuff. There is nothing in the head. I know a lot of people are interested in that. Instead, all you get is a magnet. And the magnet goes to the magnet on the stock, which you can kind of see here, which you can see up here if you are present. There's no motor in the head. When he turns his head back and forth, it's inside. He's turning the whole center of gravity. The whole time I'm taking it apart, I'm also still trying to make it functional, because I did want to put it in a clear thing, and I did want to look at some signals, which I do get to do at some point. Here's where you start to see that there are only 2 motors, and the differential gear driving can make it turn around, and if you do them on different speeds and different directions, you can get all of the motions you want from those 2 stepper motors. The arm comes off very easily. Once you take off the head and you take off the electronics, the little magnetic part that holds the arm, actually just a little piece of plastic with some with a spring and some nice wheels to make it go around and see. It's not shocking, but it does stick to the head really well. On the bottom, there is the inductive coil, which is used for charging, which is pretty nifty on its own. If you haven't seen an inductive charger, basically you get a bunch of wires, you coil them around, you put them on another coil, and they magically, who cares? Let's get to the electronics. One thing to notice about this is that there's a big lead weight. Many people think this lead weight is what is a counterbalance to him moving, but that's not how it works. Instead, the lead weight is always falling. The center of gravity is what moves him. It's why I wanted the clear one. Mentally, you think that the weight is lagging, but really the weight is leading. So other people looked at the mechanicals. Let's get to the board. Finally. This is the top of the board. This is where most of the interesting stuff is. I don't know if you can read that. I can see you got a lot more interested in trying to find those numbers. Let me help you. Yeah, does everybody keep a list of package marking in their head? If so, can we talk? Because some of these really made me crazy. So let me do that nicer. Bluetooth, CSR 1010 is the Qualcomm chip. Really nice, really nifty, really new. And yet there are dev kits, even though it's a Qualcomm chip. That's attached to the 16 megahertz crystal and 5K I2C EEPROM. Over here, we have the processor, a Cortex M4 with an FPU. What in the world do they need to do with that? I would say that's where the sensor fusion is, except that their inertial sensor is the Bosch NI055, which is 6 degrees of freedom, accelerometers and gyros, and a temp sensor, but we're not going to do that. And that can include sensor fusion in it. So I have no idea what they're doing with that ginormous processor over there. I really want to know. They do helpfully provide a few test points, nicely labeled I2C, SDA, and SCL. That's got to be some goodness there. Voltage regulator is interesting because of the inductive charge. That chip was not marked, and only the help of an electrical engineer who looked at the backside and said, oh, all of these passes has to be powered. Lithium ion charger, op amp, some power thing. You know, I got bored at that point. The motor driver is not an I2C motor driver. It's got 8 pins within the cover. But that's the cool stuff. 2 RGB LEDs, PWM controlled. There is another LED running around. It's a little tiny blue LED used for guidance. What? I could find nothing that indicated an IR sensor to me. I did not find pads. I think it was all a ruse, but I could very well be wrong. I'm not sure I know what all IR sensors look like. So I do invite you to check out the board. In fact, if you want to, have at it.
You see the LEDs in the case?
Very well, yes. They're nice and bright. And they're almost, those 2 LEDs that are RGB are in sync. So if it turns blue, they're both blue. If it turns yellow, they're both yellow. And that definitely helps with getting through the opacity of the shell. The shell is not particularly opaque. Actually, it'd be a good thing to ask around. Yes? Is it the BMI? The BMI 055 is a 9 degree of freedom. There's another one that's a 6 degree of freedom. I have the label later.
Okay, so I'm just wondering, because there's like a, you know, 055
So for those of you online, the question is which is the actual part number, because that affects whether or not it's got sensor fusion. And it is true that these spherical people could have done their own sensor fusion. As I will sort of allude to later, if it were me, I would let the Bosch people do it because they did a really good job. But that's weird. So looking at the back side of the board, I was still, you know, at every point it's like, am I going to get this back together? Happily, the board is just connectors. It's really easy to take off and on. It's been on and off a whole bunch of times at this point. Test points, gooey test points. SPI test points, those lead to the Bluetooth chip. And I believe that's what they're using for programming on the Bluetooth chip. I don't know how they're programming the I2C EEPROM, but I have my theories. It's not through the I2C test point.
Try that pre-program.
They could buy it. I don't know what they're storing in it yet. It's not the code for the BLE. It's not big enough for the code for the BLE chip. 5K bits, so 16K bytes. Let's see. Connectors, they are keyed, so you can't put it in backwards. Yay! Software engineers everywhere go wild. The motors connectors are exactly symmetric, which is also nice. This strangely does not connect to anything once it's in the part. And this capacitor required its own little mechanical room. So, pretty cool. We will be looking more at that P4 because there's nice goodness there. One of the things I did in looking at that P4 was to note that on the silk screen on the other side, it said PRX and PTX. It also had standby and power, but who cares about those? I mean, you give me an RX and a TX, and I'm like, okay, 0 port, sweet. I hooked up my Celier, and off we went. He does not like being connected when he is like this. He gets his motor goes crazy because the motor is fed back not through encoders or anything expensive. Instead, they have the inertial sensor. So they tell the motor, I want to be level. And if it doesn't get level, the inertial sensor says, I want to be more level. And if you're holding it, it freaks out, which is fun. Hey, look, I'm done. Okay, I'm not really done. The next slide is, can I go on? Because I wasn't sure how long you wanted me to go. This is me. The plan for this is to write more in Element 14. I'll probably do a blog series where I go over the different hardware and firmware parts and what I speculate will be happening. And then I do have a podcast, which if anybody doesn't know about the podcast and wants a sticker so they remember it, let me know. I have lots of stickers. Okay, so you do want me to go on, right? Okay.
Yes.
I had 2 chips that I spent 3 days trying to figure out. The first one was marked 134A or Lambda 1426095, and I could not find anything. I knew that it had lots of pins. It had 16 pins, 7 plus 1, 7 plus 1. It was too big to be the MEMS sensor because why do you need all those pins if you're doing everything digitally? But too small to be anything else. Eventually, it turns out it was the MEMS. The other one that I still don't know is this JA33. I stopped looking at it because the fat pin on the other side indicated that it probably had thermal properties, and so it was probably something to do with power. I'm looking at all the hardware engineers in the room. Who's going to raise their hand first and say, it's a
Power chip.
Thanks.
Voltage regulator.
So that's the sensor number. Is that sensor fusion or not sensor fusion? So they must be using the Cortex M4 for their sensor fusion engine. Personally, I think that's a little inefficient, but maybe that's what Sphero did. The whole thing is based on the Sphero robot, which came out a while ago. It has some new bits, but it's not especially new. A lot of the interactions are the same. So, maybe they inherited that. But this is the Bosch chip, and it is the one that I couldn't identify. I got a hint to search for the lower numbers instead of the upper numbers. I was focusing on the 134 instead of the 095. And it has a lot of grounds and do not connects. It is in I2C mode. It also has a couple of SPI modes. But ohming it out indicated definite I2C. These are the technical information for that part. But I also have the Adafruit 9-axis version up here because it is really cool and a great way to learn about inertial sensors. One of the things that they put together was how to calibrate an inertial sensor. It is remarkably difficult, and one of the things I heard about this board was that it was kind of a beast to actually manufacture. How you orient the sensor on the board, how you know it's oriented, all these things are tricky. And that chip over there, or that board and its chip, is 9 degrees of freedom. The accelerometers are 3, the gyros are 3, and then that one has magnetometers. You wouldn't put magnetometers on BB-8 because he's got the motors, and the motors are just going to trash everything. He's not going to be able to move and know what direction he's pointing. And really, he doesn't care what direction he's pointing. Adafruit is also a really great place for like thinking, okay, I have accelerometers. How do I know what my tilt angle is? Go look at their sensor code. It's really good. Kevin did a really good job on that, and they have nice explanations. Chris Gamble would like to know what sensor fusion is. Sensor fusion. Okay, so you have accelerometers and you have gyros. And the accelerometers kind of tell you which way is down. And they don't do a whole lot more than that. Sure, if you're in your car and you're zooming up, they will tell you that you're zooming. But 90%, 99.5% of their life, all they answer for you is which way is my gravity vector. The gyros, on the other hand, are a very different sensor. They measure, are you spinning? Are you turning? Now, turning doesn't mean, am I spinning around like a desk chair? It can mean around a joint. That's a gyroscopic motion. This is a different gyroscopic motion. Actually spinning around is a different gyroscopic motion. And there you have X, Y, and Z on your gyro. Gyros are boring unless you're moving. Accelerometers are kind of not great if you're moving because they don't understand much beyond gravity. They really like to know gravity, and if you're moving, you may be getting more acceleration than just gravity. So you have these accelerometers that are good when you're stopped, you have these gyros that are good when you're moving. What you want to do is combine these in a way that accentuates the positive of each of these crappy sensors, each of these inexpensive sensors. And so what you use is a Kalman filter usually. And when you put that algorithm together, it's called sensor fusion. If you added magnetometers, which you can think of as somebody pointing a flashlight from one direction, and no matter how you turn, you can see which way is that strong magnetic flux called the Earth magnetic field. And so you get this flashlight. And now you think about, okay, am I stopped or moving? And I always know that that way is that way. You get a better sense of fusion. If you add something like a barometer, which tells you the relative height, it isn't really good at telling you, are you on Everest or are you in San Francisco, because weather has a big impact on it. But it will tell you, I climbed 5 stairs or I climbed 50 feet. And that adds into your sensor's fusion because it will tell you your accelerometer must have a little bit of error because it didn't notice you climbed. Or your gyros have errors because they say you're moving, but everything else says you're stopped. So sensor fusion is about knowing where the errors are and assigning them correctly or best guess. And that gives you a better overall solution. That was like my whole other talk. Is that okay?
Can you go over all the formulas?
I could go over a number of the formulas, but instead, one of the other parts from the solid talk is talking about how you and your inertial sensor have to be in the same reference frame. If it's pointed that way and turned upside down halfway, and you think you're going this way, it's not going to give you X, Y, and Z what you expect. So what they do in this is they make you point a blue LED at you, and then now you are in the same inertial frame as the robot. It's a very clever solution to a pretty difficult problem of how do you and the robot agree on which way is X, which way is that way. I do have these to play with, so yeah. STM, Cortex, M4, lots of flash, nice speed, 8 megahertz, pulled up to 72 megahertz. I did a little bit of ohming out. There are some more motor connections and some, the LEDs get driven from here, PWM as well. The most interesting part about this are those, which go all to a connector. And anybody who's a software is like, oh, really? I have access to your internals? Probably not. I haven't tried it yet, but I think this processor has a nice lockout feature that you can't read back the code. Maybe if I get some time next week, I will see if they use that lockout feature and if it's really as good as it's supposed to be. But for now, what? Could I overwrite the code or overwrite the lockout? I could overwrite the code, but if I don't know, that does imply that I can reproduce their code. And maybe eventually I could, but I'm not quite willing to break my toy yet. Motor driver, it is all PWM controlled. I was a little surprised I would use an I2C, but you know, they had pins to burn and apparently timers to burn too. He is located right next to one of the motor pins, motor sets on the board that goes through to the bottom. The other set is way over on the other side of the board, the kitty corner across. So clearly they kept one part clean and then dirtied the other half of the board. It was a little bothering. I2C EEPROM. This half is entirely connected to ground. This is also connected to ground, so they must be writing to that all the time. I don't know why you do that, but it does make me want to sniff those nice fat pins that I can grip on with my Celio. The batteries, there are two of them, both 3.7 volts and both 1.3 watts. Do the math yourself. I'm not an electrical engineer. So when I measure VBAT, it's between 7 and 8 volts. I suspect that they run the CPUs off of one of these, which I know is not very good for batteries, but you know, the CPUs take tiny amounts of power compared to these motors, and that's a much lower voltage drop. It is attempting to be slightly power efficient in many ways. It goes to sleep very quickly, and somehow it wakes up in a way that I don't understand. You get close to it, you have to turn the app on. Now, if you just play with it, then you whack it or something, it doesn't turn on. But if you get close to it with the app, it turns on. And not so close that it could be accelerometer. So somehow that Qualcomm CSR BLE chip is noting that you're looking for something and then it wakes up the rest of the processor. It's the master as far as power is concerned.
The older ones use half of turn on that.
This doesn't seem to be accelerometer based.
Okay.
I've tried to sneak up on it many times.
Well, even with the older ones, you had to give them a fair tap. That was how the ones turned on.
So the old ones turned on if you tap them, and that's an accelerometer interrupt. It's really easy to implement that. But this one, that doesn't seem to happen. It doesn't turn on unless the app is running. The app has to be in connect mode, and so it has to be searching, and then even if I'm 6 feet away, it connects. So I don't think the accelerometer is getting my footsteps from that far away. I don't have to tap it anymore. I mentioned there are test points for the SPI signals. I can only find a manufacturing use for it. This is the EEPROM, which I thought was SPI, but have since determined is I2C, so it's just, you never saw that part. Oh, right, this is up here because, not because of the EEPROM, but because they put the SPI on both sides for me. Those pins are the same as these pins. The interesting one here, MOSI, MISO, clock, slave select, those are all nice. But why is there one marked SPI? I mean, it's like, okay, we've already done all the SPI pins. Why? My theory is that selects between the manufacturing SPI and the processor driving the SPI lines, because you don't want to be driven by both a manufacturing fixture and by the processor. I did a software block diagram. I really like block diagrams. It's sort of my thing. But once I broke it all down, it wasn't that exciting. But for all of it, this is a simple block diagram. The product is pretty neat. And not just because I like the robot, but they did a good job with the engineering. It doesn't look super cost reduced, but they certainly are are going to be the next generation. I think they're going to take a lot of those chips and make them cheaper. And I did say that, oh, sorry. The motor driver is definitely a stepper motor driver. And it was more expensive than its DC motor driver twin. So I don't know, I really think they are steppers. I took the RX and TX and hooked it up to my Elecia, and also that standby signal. The standby is what wakes up the STM processor. The TX is from the STM. So this is the processor transmit, and processor receive is from the BLE chip. I looked a little bit more. One of the first sets are all paired, like a command and response structure. Then later, we end up in this mode that's spewing data, more like a sensor. I wondered initially if this was the MEMS sensor I couldn't find, but now I'm sure it's between the two processors. The early one, you know, it looks like a command, sort of. Yeah. But then I started looking at those 50 hertz, 50 millisecond updates with 20 hertz, which is a nice, fast enough for inertial to keep up, and yet not so fast that you're going to drown Bluetooth. I already knew that it was sending inertial data over Bluetooth because I got those pictures of it sending accelerometer data. So I looked more and more at the packet. It's 34 bytes every 50 milliseconds. So I looked more at the packet. Hex is awesome. I just love Hex. Some interesting stuff here. I had it sitting, doing nothing on my desk. Its motors weren't going, it was just sitting. And that got me those. So I turned it upside down because I wanted to see where the accelerometers were. And so I then turned it on its side, turned it on its other side. Now, each data collection, you know, takes about 2 minutes. It's not trivial yet, but I have a path to get there. Once I did all that, I realized that the first several bytes were always the same. The last one of those is the same number as the rest of the bytes, which is how I would do a command packet. You do want to put the length in there somewhere. The FFFE is different than the command response ones, which were FFFF. And then I took those and I took all of the remaining 29 bytes and put them into int16s. I also put them into floats and UNT16s and double. Okay, so I tried everything, but I think it's in 16s. And the reason is because some of these make a lot of sense. When I took these three, when I went through and looked at the magnitude of each triplet, so it squared and took the sum and square rooted, these three together are always about 10,000, which gravity vector being what it is pretty constant. So I think what happened here is that I messed up something somewhere. And I turned it up, and instead of turning it over, I must have turned it on its side. We will find out when I do it again tomorrow. But I'm pretty sure these are accelerometers. I am pretty sure that these are some sort of motor feedback, because it was only the normal ones that the motor wasn't going. Once I turned it upside down, it kept trying to right itself, and its motors were going wild. Could I disable the motors? Maybe. I don't know. I'm a little iffy on that one. So my next step first is to write a Python script to parse out those packets so that I don't have to do this every time. It's a pain in the neck, and I use Excel. It's awful to do it. Python is the way to go. I2C is the test points on the board. I can see between the MEMS sensor and the Cortex processor. So I can sniff the packets from the sensor directly, and I know what those look like. If I know what those look like, then I can easily pick them out of the BLE transfer packets. And I walk through the code in the STM. That would be fun. I can probably overwrite it for sure. No chance of that blowing up in my face. What? if they're doing a sensor fusion algorithm, pretty hard. I would not trust a reference design for sensor fusion. It is a much harder problem than you might expect. Tuning it is really hard because they create these sensor fusion algorithms to be able to deal with situations where you're in space, where you're on a boat, where you're going fast in a car, where you're walking, and you're doing pedometer sorts of things, and then you also have a rolling robot. You have to tune your algorithm in a sensor fusion. And that is where it all goes horribly wrong. Math is not that hard. I put a slide up at the beginning that went to a Kalman filter. It's a nice explanation, and yet still at the end, when you implement it, you'll be going, oh, what did I do? I did take some time to look at the BLE characteristics using light blue to look at the formation. I was a little worried that they were going to just do the simple BLE UART thing, which is such a cop-out. But they have nicely formed gap characteristics, and I'm sure those could be mapped to my Python packets when I do that. They have a number of different characteristics, and read and write, notify, all the good stuff. So that does lead me to, can I start controlling it from my computer? Can I start doing things where I do the BLE instead of the app? It is pretty promiscuous. If you get near one and it's off, and you have a BLE-enabled phone and the Star Wars app, it'll pair with you. It's not permanently paired to anything. It's really, it likes everybody. And then I want to know what makes it wake up when the phone is near. Is that the CSR staying on all the time in a sleep mode or something cooler? There's lots more to do. Let's see how much time I get. And that's really the end. Any more questions? Yes. What do I plan to do with the secret? The secret?
Secrets that you discover about this.
Well, I'm going to write about it. I mean, I bought this as a business expense. So I will write some for Element 14, and I'll talk about it on my blog, and just play with it. I'm not too worried about the secrecy part. A lot of the Sphero has already been torn apart, and they haven't fussed before, so we're going to hope they continue that. And I do want to emphasize that I think this is a really cool product. I took it apart because I was curious, and now I really want to spend more time taking it apart because I think they did a good job. I have talked to someone who is loosely affiliated with them, who I will not name because that would be wrong, who seems to find it all very amusing. I sent him the slides, and I did offer, was there something that I shouldn't delve more into? And maybe he was just very wise in not admitting anything, because of course that's where I go first. But they seem to be good kids. And I don't have any particular plan. I'm playing with it. And the week between contracts, next week, I may not get to play with it a lot more. We'll see. Anything else? All right, well, I'm Elecia White. My podcast is Embedded FM. It's like the Amp Hour with Chris and Dave, except not.
So one more round of applause for Elecia. One thing we did want to offer, we did mention on the website, if there was anyone that wanted to do a lightning 2-minute thing about what they brought, I did forget about that at the beginning. Sorry about that. So anyone who was interested? No?
He was worried I was going to go for an hour. That's the real
you never
problem.
know. You never know. Okay, well, definitely check out the robot. I'm going to be playing with this thing. The robot is amazing. There's more beers. If there's not beer there, there's beer here. Thank you for showing up. We always appreciate it. Please tell other people about the meetup.com site, or don't if you want to get on there first. We do appreciate you all signing up right away. And we're always looking for speakers too. So if you're interested in talking we'd love to hear more. And also, Matt often has meetups here in this office doing kind of tutorials, stuff like that on weekends. So that's another good thing. Matt's going to do a 2-minute lightning talk.
No,
He's never gone more than 2 minutes.
No, I never get a chance to do anything handwave because I always promise that I won't. So just really briefly, towards the end of this month, I'm planning a workshop, which is actually running out of this office. It's listed on Meetup. Actually bringing in a bunch of stuff to actually take people through the sort of proper process of actually soldering a bunch of stuff together and actually physically building some stuff. So I've got a heap of soldering gear. I'll actually take you through reballing VGAs and actually hand soldering VGAs onto a board. I'll bring in my reflow oven and actually show you how reflow works and the different temperature profiles for reflowing things. If I get some time, I'll bring in. If I get some time in a truck, I'll bring in my pick and place machine, which would actually be kind of cool, and show you how to reel things up and actually populate boards and kind of the fundamentals of that whole process. But I've been running a number of different workshops. They're free to the public, but they do fill up really fast. For those people that weren't able to make it into the one which is happening at the end of September, time frame is kind of middle of October for me to probably do it again. I got really busy over the summer. I was running the workshops a bunch, and then people were screaming at me because I stopped for a while, but I did have like work to do. So, but if you're interested, if you go to Meetup, you just kind of look me up on there. I also do a couple of other workshops. I did one on the ESP8266 and kind of taking people through setting up some basic Wi-Fi and building an actual board with that. I'll actually do something which is much more hands-on, actually hand-soldering that and actually building the ESP board into a real system. I did that one down in Pasadena, taking people through actually designing circuits and fundamentals and stuff like that. So it's kind of hand-wavy, but it's free, so it's not really hand-wavy. So that said, thanks to Chris, Elecia, thank you. Tom, absolutely amazing. Thank you guys again. Big round of applause for these guys, and thank you guys so much. There is more beer. If that looks like it sparks, there's actually more beer in the fridge. Feel free to hang out, mingle, talk amongst yourselves or with other people. Yeah, thanks.
Does anybody know where BB-8 landed?
BB-8 does get around.
He really does.
It's promiscuous.
He's very promiscuous.
Oh, you know what? I have the body. I think I have my body on my
top. Okay.
Do these legs
Fred more than
wave goodbye.
Okay. Yes, you should do it, Loki. I really like that.
Say how many